Okay, so this is really a very, very short presentation just to kind of introduce you to the electromagnetic spectrum that we use in spectroscopy, okay? And just an introduction to spectroscopy in general. In general, how many times have I said that? Okay, anyway, so spectroscopic techniques are generally used for, again, generally, for organic chemistry. And what we do in there is try to determine the structure. Sometimes we also study just some properties of molecules, but mostly it is for determining the structure of any organic compound, whether you have made it or whether you have isolated it from nature, it doesn't matter. The goal is that you should not destroy a lot of the sample, because sometimes you're working with very small amounts, but sometimes you can't help it, okay? The sample does get destroyed in the process. So we're going to be doing 4 spectroscopies if possible. So one is the ultraviolet and visible spectroscopy. So together, ultraviolet and visible are 2 different regions of the electromagnetic spectrum, but we do them together. Then we also will study the infrared spectroscopy, which is IR, okay, the infrared region of electromagnetic spectrum. And then we will do mass spectroscopy if possible. Anyway, mass spectroscopy does not depend on the electromagnetic spectrum, because in this case, you're just taking the molecule and you're just bombarding it with electrons and breaking it apart. So it has nothing to do with electromagnetic spectrum, but it is part of a spectroscopic technique. And then finally, we will be doing the NMR, which is nuclear magnetic resonance, and that also uses the electromagnetic spectrum. Okay, so before I get into the electromagnetic spectrum, I just want to remind you that you must have done all of this before, that you have a wave, okay, because light travels in wave form, which is the electromagnetic spectrum that we're talking about. So here is a wave. This is a wavelength, a crest up and a crest down. Frequency is the number of waves passing through in 1 second. So that's frequency. Wavelength and frequency are inversely proportional to each other. Frequency and energy are directly proportional to each other, because remember the quantum model, and the quantum model states that in any kind of a wave, you have energy packets, right? Quanta going on. So those are traveling on the wave. So you have quanta, and then you have frequency, you have wavelength, all of these relationships you have to remember, which is really not all that hard, okay? But anyhow, let's come back to frequency and wavelength. So these are inversely proportional to each other, because the longer the wavelength, then the less the frequency. Okay, so the way that works, in case you're interested, is that if you have a long wavelength, then here, if this is a 1 second time, then you have less waves going in 1 second. So the frequency is less for a longer wavelength. If the wavelength is shorter, then the frequency is higher, because now you have more waves going through in 1 second. Okay, so that's the relationship between them. So which means that wavelength is inversely proportional to frequency. In order to remove the proportionality sign, you have to add a constant, and that constant is the speed of light. Okay, so that's our constant. So this is our formula that we use in order to calculate the frequency of any wavelength, any radiation. Okay, and so you can use this formula for that. Now, frequency is directly proportional to energy. Okay, so and that's because of the quanta. All right, so that's another relationship you have to remember, which is coming up in the next slide. So here is the electromagnetic spectrum also, and here is the fact that the energy and frequency are directly proportional, and the energy per photon. So when you remove that proportionality constant, you have to add a constant, and that constant is going to be Planck's constant, okay? Because Max Planck was the one who kind of developed the quantum model, okay? And so that's the equation that you use, E is equal to h nu. So these are your relationships here, okay? And this is the electromagnetic spectrum, which starts from radio waves. And why does it start from here? Now, this is just assigned randomly, okay? It's not that it came from above or something like that. No, scientists decided that these were going to be called the radio waves, then the microwave, infrared, visible, ultraviolet, and gamma rays. And these distinctions were made according to wavelengths, okay? Or you can do frequency also. So here we'll just use wavelength. This wavelength is given to you in centimeters. So you can see radio waves are really quite large, okay? And radio waves for that reason also were the first one to be used for anything. So radio, like in listening to a radio, right? That's how it was used. Anyhow, so here is really a large wavelength, so which means the frequency is very low. Here you have a very small wavelength, so the frequency is very high. Short wavelength, high frequency. It's a opposite relationship. Energy, on the other hand, is increasing as the frequency is increasing. I like direct relationships. So when you increase one, you increase the other also, right? So energy increases with frequency. So what we are going to be doing is when we talk about the different spectroscopies, I will be mentioning about the wavelength, okay, because a lot of these things that we will do is to deal with the wavelength, the IR and the UV vis. So which means that we will be talking about energy in there, okay? We will talk about energy in NMR also, which uses radio waves, okay? So we'll talk about that as well. So that's why you kind of need to understand the electromagnetic spectrum, okay? So again, let me go over this. So you have radio waves, and then microwaves are more energetic. More energy is infrared, and so on and so forth, okay? Between here somewhere is also X-rays, which I'm not talking about because X-rays is a whole different kind of technique. And we don't do X-rays in at our level, okay, right now. So in any case, so all of these spectroscopies we are going to do. Ultraviolet visible together, IR in one way, and radio waves is not a spectroscopy, but we use this in NMR, okay? So we use infrared, and in infrared you will see molecular vibrations, and UV vis we are going to see electron transitions happening. That's, I will explain all the theory to you when we do those individual spectroscopies, okay? But these are the things that are used in those spectroscopies. I need you to know this, okay, in case I haven't said it already. Okay, so what are the regions? Now, in case you want to remember this, this is fine, but this will come up again when we start doing the spectroscopy. But here is the wavelength for UV vis. Here is the wavelengths for IR spectroscopy. But in IR spectroscopy, we actually use wave numbers, which is 1 over wavelength. So that's kind of frequency. And in NMR, we use frequency, not wavelength, as our measurement, and that's in hertz, okay, or megahertz. So anyhow, that is our spectroscopy regions that we're going to be learning about. I think that's about it. So make sure you learn the electromagnetic spectrum. If you don't know how to calculate wavelength versus frequency, that's no biggie for me.